Hello everyone, welcome back. In the previous video we talked about the definition of the angle and radian measure along with some visualization through the notebook I created. Let's review all these, this time from the textbook. Of course we are going to do that as briefly as possible. Here is the convergent factor 180 degrees over pi and the factor pi of 180 degrees depending upon what to change, converting what to what. And then now let's look at the periodic behavior of the angles. Here in figure 6 you can see that 30 degrees and 390 degrees and negative 330 degrees are essentially the same. You can add or subtract 360 degrees or as a matter of fact any multiple of 360 degrees. The reason is because adding or subtracting 360 degrees will not change the direction because you're coming right back to your original place. So we have the periodic behavior like this. Our textbook author calls coterminal angles, but that's not really important. The name is not really important. Important is 360 degrees. Even more importantly, 2 pi, because we're going to primarily use radian angles in this course. So radian measure is more important. You can add or subtract any multiple of 2 pi without affecting the terminal ray. Here's another visualization. Any multiple of 360 degrees, even if it is really rotating many more times. Okay, that was a quick review, and let's move on to geometry examples. Example 1. Arc length formula, S equals r theta, where S is the arc length, or theta equals S over r. And that's actually coming from the definition of the angle, radian angle, theta equals S over r. So the bottom box here is actually the definition. S can be either positive or negative, counterclockwise positive, clockwise negative. However, if I throw away this positive negative part and then look at only magnitude, then you get this arc length formula, theta equals S over r, consequently S equals r theta. Next is the area formula, and it kind of goes like this: A equals 1/2 r squared theta, and the visualization here is given in figure 11, but let's use the notebook I have for a little bit better control. And okay, here is the arc length formula, and that's pretty much straightforward. And let's talk about the area formula. Well, okay, here's a visualization. A little bit difficult to visualize with this one, so too small. Okay, this is just about right. Theta is of course 0.131 pi or something. Well, that's not really that important. The really important thing is how much portion does this sector has out of the entire disk. That's given by theta over the entire angle 2 pi. Theta over 2 pi. That's the ratio. So that's the ratio you have to multiply to the area formula. So what's the area of the entire circle? Is pi r squared, isn't it? And then the ratio theta over 2 pi represents the area of the sector occupied in entire area of the disk. So we end up with pi r squared times theta over 2 pi. After some simplification, we end up with 1/2 r squared theta. Pi in numerator and pi in denominator cancel each other out. So please remember these two formulae, arc length formula and then the area formula. And then let's do a couple of exercises. Exercise 1, let's find out, estimate the distance that Earth travels around the Sun in a day. Okay, assume 1 year is 365 days, approximately speaking, and the orbit of the Earth is a circle of radius 93 million miles. Okay, everybody knows that the real orbit should be elliptical, so it's a little bit different from 93 million miles, but in reality, the elliptical orbit is really close to the circle, so it's okay to use circle. And also, the real Earth's year is a little bit longer than 365 days. Because of that, we have leap years and things like those. In any case, as an approximation, we can use this kind of computation, S equals R theta, which is the formula we'll have to use. And the R is 93 million miles as given. And theta is something you have to think. It takes 365 days to cover entire rotation, so 2 pi rotation. So in each day, it will be 2 pi over 365. That is the angle. So calculation yields about 1.6 million miles. Here's a little bit more accurate computation. Instead of 93 million miles, I use a little bit more accurate radius. And then instead of 365, I use a little bit more accurate Earth day, including those leap years and things like those. We end up with, well, about the same value as a matter of fact in terms of effective digits. Okay, one problem is done. Now let's move on to a problem that we'll have to utilize the area formula. Okay, here we go. Find the area of the region swept by the wiper blade, and here's a picture. And the region swept up by this wiper blade is not really a sector. We have a large sector with radius 34 inches and small sector that is left behind 14 inches. So we'll have to calculate the area of the large sector and the area of the smaller sector and subtract one from the other. And here goes the strategy. Area is area of the outside minus area of the inside. Area for 34 inches minus area for 14 inches. So 1/2 r squared theta for 34 inches minus 1/2 r squared theta for 14 inches. You can factor theta over 2 out, and then we have 34 squared minus 14 squared. Now, okay, that's 34 squared minus 14 squared, and 1/2 was there before. What is angle theta? Here it is. We have to use radian measure in order to use that area formula for radian. So you have to convert this 135 degrees into radian. How do we do that? Conversion factor pi over 180 degrees will do. Degree cancel out, and we gain pi. Excuse me. If you do this computation with handheld calculator or anything, then you're going to get approximate area. 1130.97 square inches. Okay, we went through a couple of exercises. Now let's resume our discussion, and this time let's discuss angular speed. Our textbook also has angular speed problem, but it doesn't come with an animation, so let's stick to the notebook I created. And this is a visualization of a circular motion with same speed. And we are looking at actually two types of speed here, two types of rate of change. If you look at how fast the tip of arrow is moving, then you're looking at something called linear speed. So it is measured by the distance it traveled over time. It is v equals to delta s over delta t. Delta s is difference of arc length, delta t is difference of time. But if you look at how fast the angle is changing, you have to look at the first one, omega equals to delta theta over delta t, change of angle over change of time. It is traditional to use omega for angular speed and v for linear speed, linear velocity as a matter of fact. Now what is the relationship between one and the other? Here it is, v equals r times omega. Why? Well, here's a quick proof. V is given by delta s over delta t, the difference of arc length. And the difference of arc length is, what is s? R times theta. And r, the radius stays the same. So factor this out, then we have delta theta over delta t, and the difference of theta over difference of t, and that's r times omega. That's the proof actually. And if you're in physics class or if you have some background in engineering, then you'll really see easily. Even if you do not have really good background in physics, you can still see how things are going. But if you're not getting it, it's okay as far as this course is concerned. You can simply rely upon V equals R omega. By the way, here's the visualization. We're looking at two different radii, and we are looking at blue and red. And then please note that red arrow is traveling much faster than the blue arrow in terms of the linear speed. However, in terms of angular speed, they're the same because they're following the same same terminal ray. And then the ratio is, well, omega is V over R. So there you go. Okay, is there any exercise problem regarding the angular speed and linear speed? Okay, let's go over to this example 2.6 here. A biker pedals 40 RPM. Find the angular speed for the wheel socket. Find the speed of the bike. Okay, so basically what you're looking at is, let's see, this pedal is 40 RPM, so that's angular speed of the pedal, and then the gear of the pedal, which has radius of 4 inches. And then because that's tied to its chain, this wheel socket is tied with chain to this a little bit larger this pedal gear, and you have to use that to figure out the angular speed of wheel socket, which has radius 2 inches. Now if you find out that angular speed, use it 13 inches to find out the linear speed of this wheel, and that speed will be the speed of bike. So this is a multiple problem, and let's go. Part A of the problem. Okay, linear speed of the wheel socket is gonna be the same as linear speed of the pedal because they are tied together with this chain, you see. And the problem did not ask you to find out how fast this chain is moving. The linear speed of the chain was never asked. Well, you could find out if you want to, because after all, we have this formula here, V equals R omega. Omega is given for 40 RPM, and radius is 4 inches. But here in this case, we are looking for the angular speed of wheel sprocket. So we have to set it up equal to the other omega. So this linear speed R omega for wheel sprocket is equal to the linear speed R omega for the pedal. So 2 omega is equal to 4 omega, where the first omega is for sprocket and the second one is for pedal. And the second one for the pedal is 4 times 40 RPM. So you can find out the angular speed of the wheel sprocket is 80 RPM. It fits your common sense, by the way, and pedal is twice as large as wheel sprocket, so wheel sprocket must turn twice as fast. Okay, that's part A of the problem, and let's go to part B of the problem. Find out the speed of the bike, which is the linear speed of this big wheel. So what is it? V equals R omega. Again, we are using the same formula, and R is in this case 30 inches. And then 80 we just found out, so multiply and then you get the answer. Turns out it is about 1 mile per hour.